Subscribe now.
Okay, hope I'm audible, everybody.
Yes, sir, you're audible.
Hmm. So today in this session, I'm sure most of you students who are present here today have already some kind of background related to the rocketry, drones, or robotic stuff. So it'll be easier for me to explain you the ground control station software systems and how they are built. I have taken upon a few more sessions earlier of this topic, and the response I get after 1 to 2 sessions is students were slightly able to make some of their systems. They were struggling, but that's again the great part. And the previous session was lacking a lot of coding interactions. So this session, if the fundamentals are all cleared up in the this session as of today, probably tomorrow or maybe the end of the session, we will start practicals. Like I'm going to share my VS Code, I'm going to share my editor, and all you have to do is just copy me whatever I'm doing and try to understand it. I will explain everything what I'm doing line by line as well. Okay, so I hope you all are excited. Don't just okay. I'm going to share these notes that I'm making right now, but I encourage all of you to at least write the brief of what you understood by this lecture. Um, no, it's like not really a problem. Whatever level you are at, maybe a beginner, maybe an advanced. I'm sure this session will teach you something that will be, of use to you. So let me share my screen, and then most of the focus should be on the screen. I'm going to turn off my camera. So please, if you do have any doubts, just write on the chats. And after the end of the session, probably I'm going to look up all of the doubts, or maybe in between the session. Okay. So if you don't understand anything, I'm going to come here after every 15 minutes and check if you are understanding or I'm going just blank. It is visible, and yeah. Um, Again, any kind of doubts you guys have, just please comment on the chats. What is the topic of today's class? In today's class, we are going to learn the foundations of how computer talk to rockets, how this things even happens. So this is going to be the foundation, or you can say the fundamentals, or you can say the ground level. If you are going to build a building on top of that, that is your software, ground control station software. Okay, so what happened let me start this from a story. At my time, when I was trying to create a ground control station software for our team, there were few problems, and I was really confused by that. There weren't any tutorials about how you actually build a ground control station system. I was really confused. Most of the time, they were telling me to use Pilot and maybe the software that are already existing. And of course, the telemetry that I was receiving from Zigbee, uh, the data telemetry was really different. So how would the software that I'm trying to build has different requirements would match up the software or standard software that was made for the purpose of drones. So that made me realize that okay, there are ways. Hopefully, at that time there were the ChatGPT and DeepSeek like softwares, the SaaS products, they were already launched. So I happen to have a basic understanding of what how it works. So that made me build my first software. So but there are a lot of requirements, there are a lot of parameters and a lot of factors that may eventually lead you through a difficult problem even in between. So I hope you can follow up with this lecture, but in case if you don't understand anything, you can just comment on the screen, comment on the chats, and I'm going to answer that. Okay. So what does I mean by foundations when I say serial communication protocols, data flow for ground control station software engineers? Okay, this is a little bit complex. Let's just keep it simple, keep it easy. And how I'm going to do that is, see, I'm going to explain you the complete architecture, okay, of what actually happens when you see this is your laptop and this is the rocket that your team made up. It probably took them around 8 months, 8 months of research, 8 months of hard work and dedication, etc., etc. There are a lot of things, a lot of requirements, etc. But what happens is, after the rocket that you're about to launch, after this is already on the launch pad. Launch pad looks something like this. Okay, so after it's already on the launch rail or the launch pad, and you can only see your rocket last time when it's on the launch pad. After that, it's just going to fly up so high in the sky and in so less time, like probably in milliseconds. In milliseconds, it will go there like 100 meters away and 200 meters away. So it's really fast. So you won't be able to see your rocket, but still you have to know how it feels, how your rocket is performing, how everything is working, how every component is working or not. So the last option for every team member and or every person, the last option they have is the ground control station software. And that is the important why we are learning this. Since a lot of time people think that I'm going to end up creating high animations, high end software. And what they mean by high end software is basically a software that performs, that has a lot of animations, lot of graphs going on up and on, and these things like that. Of course, we are going to include this, but our entire focus is not going to be on the screen today. The problem that happens is basically when your rocket is already 200 meters away and it's going at a speed, even at a greater speed, and it's already 200 meters away from the ground. The next thing probably you want to look at it, how it's performing, and what if the altitude sensor is giving you the right data, if the temperature is working right, temperature sensor is working right, and all of the components that you have invested upon is properly functioning. Now, if you want to get that information, where do you come? Where do you see it? You probably see it in the ground control station, this software. Now, if you end up creating high animations, high frequency, or maybe animation that takes up CPU, that takes up RAM, if you end up creating these kind of things that consume your CPU and RAMs, then probably the altitude will increase. The rocket will send the data that okay, it is the altitude is increasing, the graph is going up and up and up. And at the time you'll realize that okay, it's not updating. The rocket is coming down, but your graph is not updating. And then you realize that the high-end components that you used in your front end that cause several kind of issues, and now your GCS is not working anymore. So the team members, 12 team members, or maybe 10 team members, or six, how many other team members, or maybe if you are individual, you won't be able to see how the rocket that you have worked so hard upon is performing in the sky. And so this is what basically happens. So that's why this things, the ground control station becomes really important, and the way you design it also, the way you maintain it, that is up to you, but still that is really important as well. So let me tell you what happens. This is your rocket, okay? And I'm sorry again, I'm asking for apology before even this drawing. So please just don't comment on my drawing. It has been this way. Okay. So this is what happens. This is your rocket. This is going up. And this is your laptop. This is the ground control station that you are seeing here. These are the USB ports. One port, let's say your rocket has two kind of avionics. Firstly is your CANSAT, or I can say the payload and the avionics of the rocket as well. So these are the two things that your rocket has, and the both they have the rocket has two PCBs. One is of CANSAT that has a Zigbee to communicate the CANSAT readings, and another has a Zigbee to communicate rocket readings. Okay, so you have two Zigbees. On the ground side, on the ground station, you have two Zigbee ports connected as well. So basically, these are the sender. They send the data. These are the receivers. Some of the time, what happens is basically you want your rocket. Okay, you want to send some kind of a command to your rocket. For example, you send a command that says release. So the rocket is going to release its parachute. So basically, this is a receiver or sender port as well. So what you have to do is set up a bi-directional communication. Now, what does I mean? What does I mean when I say bi-directional communication? You are going to send the data. You are going to receive the data at any time. And as the most of the competitions and most of the cases, even if you are doing it for your own interest, the requirement should be, or the requirement that is stated as, we need the telemetry as fast as 10 hertz, or maybe even 1 hertz. One hertz means they want the telemetry, they want the rocket telemetry to be updated at the portal at the rate of 1 hertz. Now that's a challenge for setting up right kind of Zigbee as in hardware. And then after everything, the challenge that comes upon is your software. Is your software able to handle bytes? Let's say even 72 bytes that are coming from both ports at a time per second. So it's like 72 bytes coming from both ports at a time of millisecond probably, or per second. Okay, so 1 second. So your software is capable of handling all of these data and storing it lifetime and updating on the software as well. So after this session, after the end of this session, probably most of the doubts of how our softwares, or how basically these ports and our software that handles these data, how does everything happens? Okay, so we are going to discuss that in this lecture. Let's just continue and see that what are our objectives. What happens is basically we have a physical layer. Physical layer is basically the Zigbee ports, or Zigbee, or when I say Zigbee, I mean USB ports. So something that is connected to your, in the simplest definition, I can say something that is connected to your laptop. Suppose your laptop, this has a GCS that you created, and these are the ports that are kind of receiving the data from it. So that is basically your physical layer. So understand UART, serial communication fundamentals, of how when we are going to take the data from this Zigbee or from this USB ports. If we cannot even receive the data from the ports that are already connected, how would be able to receive the data coming up from the sky? Okay, so first you have to take a dummy, let's say when I say dummy controller, just take a microcontroller, attach to it, and you program it this way that it's going to send you dummy data. Dummy data means the data that is exactly in the format of what you're supposed to send from your PCB. So that is, that the data in the same format of PCB, you have to program your Arduino or maybe any kind of microcontroller that you are using to just give you the data in, probably any kind of, let's say, let's choose a baud rate. And don't worry about these terms. I'm going to explain you in this session. So let's just remove that. Okay, so I hope you all guys already know what physical layer is. It's basically something that is connected to your laptop. Synchronization means interpret and align baud rates between hardware and software. Let me get you this by an example. Let's say your friend is trying to talk to you and you are trying to understand it. But basically, he's talking in a way that is too fast for you to understand. Let's suppose you are somebody who just learned English, how to speak English, and you are trying to learn it basically at the starting. But then you have your American friend that calls you out, and you started talking to him, and he's explaining something really fast. So your brain is not able to catch up since you just understood the language. You're trying to understand the simple words. You're trying to understand for simple things in a slow rate. You understand in a slow rate just because you have learned English just now, but he's experienced with it, so he's just probably going to say something really fast that you wouldn't be able to understand. Okay, so that is what happens. So the synchronization is really important. Basically, your laptop or basically your let's say the rocket is trying to send you the data at a rate of 19200, and if you know numbers, this number is really high. So you're basically the rocket is trying to send you, or the avionics, or when I say the PCB in the rockets, the PCB in the rocket is trying to send you data at 19200. But you have set the ground control station to receive the data only at 9200. So if it's trying to hear something that should come out slow, if it's trying to expect something that should come out slow, and it is getting the output that is really fast, the ground control station won't be able to understand what the rocket is trying to say. So even though the telemetry is properly receiving at the rocket is feeling cold temperature, and the sensor is recording it. But when the sensor or the PCB sends the signal to your ground control station, hoping you would represent the values, but your ground control station is not able to receive it just because it's not at the same baud rate as of the rocket. So, somebody said, explain the UART or USB. Basically, if you are already experienced, or if you have already used microcontrollers are basically some things, they are some kind of a device that can control electrical signals in form of zeros and ones, and you can program it how they control electricity. So very small amount of electrical signals they are capable of controlling. Let's say this is a microcontroller. You want to take an example. This is maybe Arduino Uno. Okay, this is connected. When you buy this Arduino Uno, you get a port. You get a USB. Okay, so this is your USB cable, and this is the Type C. So this is Type C of USB cable. You get this, and you get the cable. So basically, USB is this cable. What you have to do is in your ground control station, when you're trying to build one, when you're trying to test if the ground control station is working, the functionalities are all right, you're not going to test your real rocket for that. You're probably going to insert an Arduino Uno. You're going to program it in a way that it will simulate the data. So that is a standard GCS building practice. We take the dummy data, we take the simulation of the data coming from this Uno microcontroller that is just attached. So it's going to send you some kind of, the readings in bytes. And all you have to do is program your GCS in a way to how computer talks to rocket. Computer talks to rocket by establishing a bidirectional communication. Now, what is bidirectional communication? The rocket can send the data. Yeah, great, Nihar. Okay, so the rocket can send the data to the ground control station, and the ground control can send the commands to the rocket. So basically, that's how your GCS is capable of talking to a rocket. Now, let me explain other things as well. Synchronization, I know you guys must have understood, since that is really important. One of the common mistakes we do after building up GCS is basically not setting up the synchronization to the right value. So the baud rate, the rocket, the data that is trying to send by the rocket is really fast, and your synchronization at the ground control station level is really slow. You won't be able to catch up. Make sure we have different baud rates available for different purpose. The most common baud rates I'll discuss about this topic further in the lecture, but let's just understand the basics first. Okay, so is there any major difference on designing CAD-CAD CubeSat in a software in real time? Basically, when you're talking about the software, the only things that matter is what kind of data is going to be sent by your PCB. You say let's say your PCB has following components that is able to record your temperature, that is able to give you altitude and pressure, these readings. Okay, nothing more, just these three readings. So you're going to design your rocket, you're going to design the ground control station in a way that it is only going to receive these three values, and it will create a graph of temperature, you'll create a graph of altitude, you'll create a graph of pressure, and you are just going to give out values that says temperature is equal to this much, altitude is equal to this much, and your pressure is equal to this much. And this is, my friends, a ground control station that you have built. Basically, the standard template of building any kind of ground control station is you should have the bare minimum features, and apart from that, the most important thing is what kind of data you are receiving and what are you trying to build. Yeah, it can handle high group of data, but it depends on what way you are trying to build it. Okay. Let's see. This is the data formatting. Compare and pass ASCII values versus binary telemetry protocols. What happens is, first you set up a USB connection. Second, you set up the USB connection to communicate at the same baud rate, so you won't have to worry about synchronization. Then comes the data formatting. Let's say the Arduino Uno is probably going to send data in bytes, but your GCS understands and is trying to print values in numeric, like integers, temperature, this much, altitude, this much. So this is integers. So you're probably going to set up a way to communicate the byte strings, the strings you are receiving in byte, to actual values, comma separated values. And that is the data formatting. Next thing is data integrity. Validate the incoming payloads using checksums to draw up the corrupted packets. Now, what happens next is, let's suppose your rocket is trying to send you 72 bytes, but in few, let's say in between, these are the 72 bytes. In between, there are several packet loss. Packet loss has many kind of features. It can happen to many several kind of reasons. Let's say you have a packet loss, so you didn't actually receive 72 bytes, but you received 70 bytes. What happened is the ground station was looking for a value that is coded to 75, like indexing. In the first value, it's going to receive altitude. Second value, it's going to receive pressure. In the fourth or maybe fifth value, it's going to receive temperature. But let's say there was a packet loss in between. So your ground control station didn't really measure or didn't really caught this packet. And that this was supposed to be your temperature. And the next value was supposed to be the gyro value. Okay. So your ground control station assumed that the temperature is lost. So maybe that might have been the gyro value. And that is really wrong, since your temperature will be showing the gyro value and your gyro value will be showing some other kind of value that was not expected. So that is what happens basically when we try to build a GCS. We have to match each and every packet that is coming from the rocket to the software. Okay, so that is checking data integrity. Now, fifth one is memory constraint. We have to manage serial buffers to prevent data loss at high transmission frequencies. Let's say you are talking at your rocket probably, and this is your ground control station. You both are talking at very fast rates. And in between this kind of communication that is really fast, you might be, let's say, take an example, you might not be understand whatever your friend is trying to say. If you're both talking really fast, even though you can understand both values, even though you both can understand each other's, you there is a chance that you might miss some packets, and that is basically the memory constraints. What happens is the ground control station is trying to receive data so fast, and it becomes so much that the cache or your cache won't be able to hold it. That gets us to a problem that says memory leak. This also means memory leak. So you build a GCS, you have to you have to focus on these things. These are our major, you can say, the crux of basically the errors that you have to handle. You have to handle the error at physical layer, you have to handle the error at synchronization, you have to handle the error at data formatting, you have to handle the error at data integrity, and you have to look out for memory constraints while trying to code your backend. Don't worry, we are going to discuss everything. Now let me just see comments and answer a few of them. Wait a second. Which microcontroller are used in satellites? Usually they go up with Pico and Arduino and ESP32. ESP32, I haven't seen anybody use it, but still, that's an option. Why we have to see a rocket failure after the rocket launch is very less time. Are we able to detect rocket failure before the GCS before the rocket launch? Yes, exactly. You can. Since I've worked with the ML systems as well, there is no hard coded way to decode it to get that your rocket is about to fall off. But still, there are parameters that you can consider, and based on those parameters, you can say that your rocket is going to fail for the launch. A common example that I can explain of is, let's say a rocket launched and it's at the apogee. It is already at the apogee, but the parachute has not been released yet. So you can assume, you can calculate this in GCS that if the rocket reached the apogee and the parachute did not receive released yet, so you're probably going to calculate that there is a problem and the rocket, the launch is going to be failed. Okay, so these are the things you can consider. Is baud rate depend on port? Like on no, the baud rate does not necessarily depend on the port, but yeah, on a certain port you can change multiple baud rates. What is corrupted packets? Corrupted packets in the lecture, in the sheet probably. Yeah, the corrupted packets is basically you're trying to receive certain data packets from the ground, from the rocket to the GCS, but there has been some kind of a problem due to transmission loss or data loss. So you were supposed to receive 72 packets at a time, but you are only receiving 71, 70, sometimes 60. Worst case, we haven't received a packet for at least 3 seconds, and that was basically due to the synchronization problem. How do satellites send signals efficiently and how the control delay is calculated? The control delay is basically called latency, and it is not necessarily calculated. It's something that you can just guess it if you are talking in random terms. Difference between memory constraint and synchronization. Memory constraint is basically, let's say the GCS was built to handle memory up to 20 MB. So you thought that 20 MB is great. It's a great bucket to handle the data that you are getting at a really fast rate. But what happened is, after the launch, you realize that the memory is going to fill up with so many, the memory is going to fill up with so many packets that you are receiving. You realized that your ground control station won't be able to handle anything, the data packets more than 20 MB. But still, this is the static one that you can go up to. Uh, of course, you can change it. You can change it yourself. So this is the memory constraint. So the memory bucket was around 20 MB. You thought that the GCS can hold up to 20 MB, but the data that was sent by the rocket was more fast. So it filled up the 20 MB bucket really fast. So you don't have any memory to just show the data. So that is basically memory constraints. You have to look out for them. And synchronization, on the other hand, is basically talking to your friend at the same time that you both can understand each other. Which is more important for mission success? A powerful onboard computer, reliable communication system with both. It's a coding scheme from full cycle redundancy code, if I'm not incorrect. Yeah, it's basically the CRC or checksum. They are both different things, but yeah, the difference is same. The purpose is same. Most AI application space seems to focus on analyzing data sent back to Earth. What are the biggest challenges in deploying models directly on board satellites? The biggest challenge is you cannot directly apply the AI algorithm on board unless and until you have a specific high-end computer for that. The mini computer that I would recommend is probably something you have heard of, Jetson Nano, and maybe Raspberry Pi 5. These are the onboard computers that you have to take in mind. Okay, if you have to program it in a way that let's say, so this is really interesting. Let me tell you about this. This is what happens. Um, yeah, onboard computer. This is your PCB. PCB. This is a different thing. This is where all of your sensors are combined. So this is a sensor thing. It is something that sends data to your rocket. Different. Okay. In our case, how do we implement AI in something like Rocket? Let's discuss that. We are going to continue after everything in today's lecture, but let's just discuss this. How we are going to say that the data we are receiving from the rocket, we can implement something as an AI model in lifetime. Lifetime means your rocket is currently in the air and it's probably either going up, reaching different stages, and going down. In between this process, how you're going to implement AI so that you can get predictions, not real values. You can get prediction on real values. Uh, the basics that I can assume is certain region or certain area. This is your rocket. You launched it. It got up to, let's say, how should I say it? It got up to maybe 100 meters above the ground. So this is basically 1 kilometer above the ground level, probably at the apogee. Okay. You programmed your GCS in a way that you trained an AI model or certain kind of data, let's say temperature, that on just the basis of what is the temperature, your AI model, or when I say AI, I mean specifically the ML model, the statistical ML model, machine learning model, can assume what will be the altitude on just by sensing something from on just by sensing the temperature. Your AI model can predict what is the current altitude, and that is the power of AI. That is the power of machine learning that you can implement here. So let's say in some kind of case, in some cases, when your altitude sensor fails, it fails, but It is sending the temperature at lifetime. So you have AI model implemented inside your ground control station. It will receive the temperature and it will say, okay, if the altitude is not coming, I'm going to assume, I'm going to use the AI model. I'm going to predict the altitude, and it is predicting the altitude in the lifetime. So that is one of the use cases how you can implement the prowess of machine learning and AI systems. That is something that we already did. So yeah, we were already focused on how to build a standard dashboard for a ground control system. We did it earlier before the competition. When we reached there, our only focus was to build something unique. We thought about how about training a model that can predict basically your temperature or your altitude or maybe other factors. Even reading from gas sensors, you have different type of gases like NO2, CO2, NOCO, these gases. So how basically what happens is I was trying to predict the value of CO2 on basis of NO2 and CO2 present in the atmosphere. So these two values were directly fed into the AI system, and it was trying to predict the value of CO2. How you do that? You give it some kind of data that is of NO2, CO, and it tries to learn that where the CO2 fits. We'll talk about the AI stuff later in this lecture, maybe in tomorrow's lecture. But yeah, let's just continue. That was an example of how you can implement space, how you can implement AI system on space like applications. You have to just think about a way that is practical and that is more suitable for you. Okay. Next thing, let's just say that about this topic, the data journey from rocket to laptop. What happens? These are the several processes that follows when your data finally reaches the ground control station, even before the ground control station. Okay, there are more comments. Let me answer. Baud rate. So then AI control rocket launches too. Yeah, up to a level. Up to a level. If you hard code it that way, only that way it can. Okay, the Kalman filter does not does that to why we need it. Kalman filter is mainly used to correct readings. You can passing data as a prompt. Great. Yeah, we pass data as a prompt. That way you can understand. The rocket. Let's say this is your the prompt engine. This is your chat GPT. Okay, you paste in some kind of a prompt, it processes the result and it gives you the output. Our GCS is basically the same. Let's suppose this is not chat GPT, but this is GCS. The rocket is trying to send something. The rocket is trying to send something, okay, some kind of a command, and we as chat GPT, or basically our GCS is trained on something to receive that only that specific command values. Let's say the rocket is trying to give you the values of temperature, pressure, altitude, and stuff, and the GCS or your chat GPT is coded to understand those values. So it will just show that, okay, this is the altitude, this it will decode the values and it will show you this is the altitude, this is the temperature raising and stuff. Whatever example suit you the best, try to understand from that. Yeah, let's just get into the topic while not wasting our time. Every ground control station is built on a single foundation, getting data from a vehicle traveling at match 1 to dashboard on the ground without losing a single critical bit. In most of the cases, most of the scenarios, let's say imagine a mission from ISRO. It is sending a rocket that has been basically developed with a team of engineers. More than 1,000 plus engineers have developed the rocket, and it took them nearly, let's say, 20 plus years. And even after that, it took around $600 million to just build some kind of a rocket like that. I don't know if the budget is right. I'm sorry. So these are the efforts. These are the efforts and money of your team. So when you invest this amount of time, this amount of the team members' times, and this amount of money, this huge chunk of money to a system, and the only way you can see it after it goes up in the sky is via the ground control station system, then you need to work so hard on this as well. So even if you lost connection, even if you lose some kind of packets or some kind of data through the rocket, your GCS is able to predict some those values on just basis of few values. Let's say the rocket is trying to give you values x, y, z, and basically from A, B, C to up to x, y, z. And in between, you lost some packets like L, M, N. Now, on just the basis of X, A, Y, B, Z, C, on just the basis of these values, your GCS should be capable enough to predict those values. Okay, that's what I'm talking about. And your GCS should be reliable enough to not break the communication. Since the communication part is not for the GCS, but yeah, the software shouldn't be laggy enough. The software should not lag. Okay, and it should work without internet. Without internet. Suppose this is the amount of energy that team have spent with this kind of money, and after the rocket is up in the sky, you're trying to say that, okay, I don't have any internet, I won't be able to receive the data. Foolish kind of excuse, right? So you don't want to do that. So GCS should be capable enough, and how to make it we are going to discuss in this lecture. Okay, we have, if communication with Earth is completely lost, can a rocket still achieve its mission using its only onboard computer? What are the limitations? Yes, in most of the cases, yeah, the rocket, basically the GCS part and the rocket part, the onboard computer that is on the rocket and the GCS. Both should be programmed in a way that even after losing communication, they can at least do the bare minimum task that they were supposed. Okay. So currently we are talking about GCS. So I'm going to tell you at the end of GCS that even after losing the communication of some data packets, uh, we are we can predict the values. Okay. About JSON, we'll tell you this is the format of data, but we don't use JSON. We use CSV. Radio sense can radio cannot sense data, but it transfer waves and how sensors connect onboard correct onboard radio. I did not understood your question. Raj, can you repeat it, please? Okay, so let's just continue to this point. Rocket sensors. So this is basically sensors inside your PCB. These are the rocket sensors inside your PCB. What happens is onboard radio. Onboard radio is Zigbee. Zigbee is an antenna that collects the reading from the sensors and it transfers to another Zigbee. So this is Zigbee 1. This is Zigbee 2. Let's say, let me give you a good example. This is antenna 1 and this is antenna 2. So this is at your rocket and this is at your GCS. So basically it is collecting the value from the environmental data through sensors. So that is the PCB and it is integrated on the PCB. So at the same time, the data it is trying to receive, it is trying to send that to the GCS. And the GCS, it's receiving the data coming from the rocket. So it is directly able to show that what kind of data the rocket is currently feeling. Okay. How do computers onboard prioritize data from hundred of sensors? They are not. If you're talking about something like ISRO, they have the capability to handle 100 sensors. On usually in our case, we don't need 100 sensors. What if sensors fail, do not send temperature data? How will AI detect it by the prediction? Well, let's say we have to set a few parameters for a sensor to work or not. You might run an AI model to just predict if your temperature is kind of working or not. Your sensor is you have hard coded systems such as PCB. It is the only role of PCB is to just integrate all of the sensors together and send the data via Zigbee. So let's say if certain temperature or certain kind of sensor is not working, you don't need AI. You just need a hard coded system. It will automatically recognize that okay, the temperature is not working. So you can just switch up another way around that. Okay, now the temperature is not working. Then altitude just take up the altitude AI that we trained, and the altitude AI will try to determine the temperature on the basis of the altitude. So you have to take up certain predictions before going on to a competition. So note 3, basically the wireless link. This is how the data transmission happens. This is an aeroplane. I wanted to build a rocket, but let's say this is your rocket and this is your ground control system. This is the antenna work. Okay, the antenna is trying to send and receive the data, and you just have to decode what the antenna is trying to receive or send. This is your ground radio. This is the Zigbee at the ground level. Okay, that is trying to receive the data or send the commands. The role of GCS is to send the data, or basically receive the data, decode the data, and then send the commands. Okay, then this is the USB serial port. See, this is how it looks like. Not this one. This is the VGA port, but this is how it looks like. Software parser. Now what happens is, let's say you are receiving data like this: 1A, 2B, 16, 1C, 3A. This is the data that you're trying to receive. How the human will understand that what is the lifetime? Let's say this was supposed to be a hexadecimal value. This is a hexadecimal value, and this is an altitude. First value of it's going to be an altitude. The software, what is the role of software is to decode this data that is coming in form of bytes, or let's say this is the data is coming at the GCS in form of bytes. The GCS is simply going to decode this data and then create something like this. The altitude is 1200 meters. The velocity is 1.2. The temperature is 25. So yeah, these are the processes that happens from receiving the data, through the environment of the PCB that is on the rocket, to ultimately decoding what is trying to feed. So the rocket says the rocket is on the altitude 1200. You can see the rocket is on the altitude 1200, and pretty much it's really amazing on how you can do this stuff just by using few programs, and that is really interesting. Let's see how it works. Yeah, this is the UART analogy, UART, or you can say USB. I'm saying USB repetitively since it is really, something that most people can understand. Understood about the, okay, there are, okay, more than 38 new messages. Sensors cannot transfer waves. Okay. Don't spam, guys. Understand about the process convert. Okay. So this is UART and the physical layer of data. The Universal Asynchronous Receiver Transmitter, UART, is the universal language between the microcontrollers and computers. So let's say you have this microcontroller, Uno, and this microcontroller or Arduino Nano. The way they are trying to communicate through each other with with your laptop, this is the Nano attached and this is your Uno attached. The way they are trying to communicate from your laptop or basically to each other is they follow the same kind of language, that is UART. that is universal asynchronous. The way this is said to be universal because it is something that if you're using UART or if you're using USB, you can recognize the data from these ports. Okay. The GCS was supposed to decode the data from bytes to a human readable format. But how will you convert the byte if the computer itself cannot receive, itself cannot understand what you're trying to say? Okay, so that's why we use UART or USB as a mode of communication. That is all you need to understand. But again, next thing is the common rocketry baud rates that we use in most of our missions is 9600, 19200, and 115200. Um, and probably this is the baud rate that you're going to use even in your, the GCS that you're going to build next time. Try to go up with, if it depends on basically how fast you want the communication to be understood and how fast you are capable, your GCS is capable enough to decode it. So probably when I was on the mission, when I was trying to build a GCS, this 1115200 was the baud rate that I used to decode it. Okay, so this is the analogy. Think of a baud rate as the speed both people agree to talk. If someone speaks fast and the other slow, you get gibberish. Okay, you're trying to talk to your friend and he's speaking fast and you're speaking slow. Both of you won't be able to get each other. That is baud rate. Just understand baud rate this way. Okay, so let's just move ahead. So format one, the ASCII telemetry is readable but insufficient. What are the pros? Human readable. Okay. ASCII telemetry is readable but insufficient. What does it mean by that? ASCII telemetry is A1, 16, 2B. This is ASCII telemetry. You can read it, you can convert it on your own, but you want actual values like altitude is equal to 153, 1523. Okay, you want values to look something like this. 1523, latitude is equal to 12, longitude is 56.78, temperature is this and that. So you need values in this kind. So even after, let's say this is your USB, this is your GCS, and it is attached on the antenna that is connected via USB on your GCS. Even though they both share the same language, but you are not a computer, you are a human. So you need to see the data in terms of this. You want the data in terms of this. So what you are going to do is in the GCS, you are going to code it in a way that is basically done by the struct library in Python. If you're guys familiar with Python, we use a struct library in Python. What it does is basically it will convert the readings like A1162B to something like 1523 and 34.64, something like this. It is not the exact conversion, but I'm just for the sake of explanation. This is the role of the ASCII telemetry or basically your GCS. This is one of the tasks that your GCS should be capable of doing. Okay, so the pro is basically the sky is human readable, incredibly easy to debug without specialized tools. Bulky takes significant more bytes per number. Since you're trying to, let's say, send 72 bytes, now 72 bytes is 72 bytes. But if the rocket is trying to send you, let's say, CSV, the comma separated values. So basically, this is a string and string takes up more byte. Let's say in terms of Python, you can say the character takes up to 4 bytes and a string takes up, a single character takes up to 4 bytes. String would have multiple characters like 2, 4, 3, 6, 3, etc., etc. So for each character is going to take up 8 bytes. So even there are, let's say 12 just characters is going to take 12 into 4. And, so you are going to have problem just like that. So all you have to do is basically try to receive the value from Rocket in terms of bytes, and then use your GCS. Your GCS will automatically, it should be capable enough to convert the values into a human readable format. That's the goal of this slide. Let's just move ahead and let me see your doubts. Why use CSV, not JSON? CSV, we used to convert the CSV, convert this format to CSV just because it's much simpler when you're trying to receive the data in milliseconds. Okay, so let's say, yeah, let's take an example. Let's say this is your CSV. Okay, this is your CSV that says 24, 62, 32, 12, etc., etc. This is your JSON altitude, let's say at a time instance. This is your altitude, this is your value, and this is that, and this is that. So in terms of decoding, what seems much easier to decode when you are receiving the data streams at milliseconds or maybe at 1 hertz of a ratio, if you are going to receive the data stream at 1 hertz, so what seems easier to decode it? In most of the cases you will see and you'll realize that CSV is really easy to decode. in terms of just passing the data. So that's why we use CSV. Also, you can directly store comma separated values, since comma separated values are nothing but a format of Excel. In Microsoft Excel, you have tabs like this: A1, A2, etc., A1 and B1, etc. So you have tabs like this. So basically, when you use CSV format, you can just open this .csv file in an Excel. So you will see that the altitude, the values at different blocks. That is again one of the reasons why we use CSV. It's much simpler to code and much simpler to store. Now let's talk about the binary telemetry. It's the industry standard. Yeah, it is the industry standard. This is the hexadecimal. And what happens is, I will recommend you, if anybody of you is trying to take participation in the in-space model rocketry competition, I would recommend you to hardly just follow this format. But not, it is not something that has been recommended by the competition, but it is something that you have to do for your own good. Basically, instead of calculating the checksum, you can still calculate the checksum, but you can do this as well to ensure the data is consistent. And it is not something that even your Zigbee is able to catch the data. There are times when your GCS is not capable enough to show that data. Okay, so what you have to do is you have to just create a header format, and you have to create a, then after the header format, you have to just store in your values like this. Let's say these are the four values fixed for altitude, these are the four values fixed for two values fixed for latitude, for longitude, for temperature, for pressure. These are the values, stored for different formats. Now since these are bytes, these are really fast to receive and decode. These are really fast to receive and decode. So if you're trying to build a GCS, just focus on this thing. Try to send the data from the PCB. Try to code the PCB in a way that it's sending data in bytes, and your GCS is receiving the data in header, in basically bytes, and then your GCS is converting the data into human readable format, that is numbers, or basically integers, or basically float. Okay, but also at the same time, just try to include this header, and let's say run a for loop in basically your ground control station. Run a loop that says whenever you see this kind of format, ff, just continue that this is a new string. Most of the time what happens is, let me tell you what happened in our cases. This was the ground control station, this was the telemetry that we received. There was no header, we just received the values from here to here. Okay, in between there was some kind of a transmission loss, so we did not receive these values. Instead we received the values from the next string, and we assumed it to be, okay, the 0000000 is going to be here, and the D12283 is going to be here. So just because we missed some packets, we assume that the original values are going to be of the next packet. Let's say this is your temperature and this is your altitude. You are receiving the values in temperature and altitude, this temperature and altitude. You said that the first value that I'm going to receive should be of temperature, and the next value I'm going to receive is going to be of altitude. Let's say in some kind of a packet, temperature you did not get temperature, you just got altitude. So this is what happened: T1, A1, T like altitude, temperature 1 and altitude 1. Now temperature 2, you did not receive. Altitude 2, you received. But temperature 3, you received. And altitude 3, you received. So when your GCS is coded in a way that it's trying to look for temperature, and after that it's trying to look for altitude, when it did not receive the temperature, it's going to assume that the A2 is temperature. So the temperature will be A2, and it will also assume that the next value T3 is going to be your altitude. And it's so wrong, right? So you are trying to decode T3 as your altitude, you're trying to decode A2 as your temperature. And this is one of the most, simplest example that I could explain you. And it is one of the most, considerable scenarios before you are trying to actually build a GCS. So if you have something like a packet, like if you have something like FF, and then temperature and then altitude assigned, and then you will say that whenever you receive this FF, just then start decoding temperature and altitude. Let's say you did not receive the FF, you by some case you did not receive the FF, so you're not going to decode this temperature and altitude values. Let's say you did not receive the temperature, so you received the FF, so you not receive the temperature, but you will still receive the altitude. And you can recognize that I received these two values, so the middle one is probably missing, so you are just going to update it by 0. So this is how you basically decode your string, and this is one of the most example or important use cases of binary telemetry. Uh, I hope you understood this concept, since this is really critical at some cases. Should I explain it again? Let's do it. Let's do it. Okay. I will try to keep it as simple as that. Okay. One last time I'm going to explain this stuff. Okay. So basically, Let's say this is your rocket, and this is the port. Basically, this is the antenna attached in the PCB. So the PCB has sensor and it is trying to collect the environment. It is trying to sense the sensor can sense the environment. So it is trying to it is trying to receive the values of temperature and altitude, just temperature and altitude. It can sense how far or above it went and what is the temperature at that point. And this is on the other hand your GCS. In my case, what was happening is in the case one, we'll discuss the case two later. This is wrong, by the way. What was happening was the GCS was trying to receive the data. It was trying to look out for altitude, then temperature. So it says that if you receive any values, first give the first value to altitude, give the second value to temperature. Suppose it in the correct case, it sent the value as altitude, comma temperature, and it was received by the GCS. And by this logic, it decoded the value as altitude equals 23 and temperature equals 30. Just take an example that it decoded the value altitude equals 23, temperature equals 30. And it is saying that the first value, whatever the first value I will receive, I will update it as, I will give it to altitude. I will say it's altitude. And the second value that I receive is going to be for temperature. Okay, so there has been some problem. I'm going to probably just switch up my mic. I'm going to change my mic in this case. Just wait for a second. Okay. This is your GCS has hard coded in a way that it's only trying to receive values. Yeah, it's only trying to receive the values in the form of altitude and temperature. So when it will receive value, let's say in a certain packet, that is what it was trying to send, it forgot there was some kind of a transmission failure, and due to that the altitude value was not received. So it did not send altitude, it just says some garbage values or maybe nothing. And also it sent temperature as 23. So the temperature was received fine. It was, the GCS properly decoded the value. But what happened is it assigned, it says the first value that I'm going to receive, since it did not receive the altitude, it just only received 23. So it's going to say the altitude is 23, even though the temperature at that point was supposed to be 23. So the next packet that was sent, the altitude was recovered, so it sent value, it sends the value as 140 comma the temperature that was 30. So since the temperature should be 33, and it says that the first value I'm going to receive would be of altitude, it did not receive any value. It assumed temperature 23 as an altitude, and the next value it received was 140, even though it was of a different packet and it meant altitude. The GCS decoded it as 140. So suddenly you will see that this is your altitude trying to go up, and suddenly this is basically, maybe this is your altitude, it drops down, and this is the temperature that was going stable and trying to just increase at some point. This went up this high. And when you see this, it's really a fault. It's really a fault from GCS. You'll get confused. Even your team members, they'll all get confused at what is happening right now. Why the temperature is showing 140 when it was supposed to be the altitude. And it is not the problem of synchronization. The baud rate, the basically rate of transmission of data that both could understand, was basically fixed. It was 9600, so it was same. It is not the problem of the baud rate. The Zigbee and the communication of your laptop to the Zigbee was with the UART, so that is same as well. So there is no problem in the communication receiving from the the Zigbee or the USB. Now where does the problem arises? It's your GCS. It's how you're trying to unparse the data. It's how you're trying to convert the bytes into something that is human readable, that is 140. So there are several techniques of doing that. What I personally recommend you to do is go with the header thing. Okay, you just say that instead of just receiving the first value and giving it altitude and second value and giving it as temperature, you're just going to say, whenever I encounter ff, whenever I encounter any kind, this header can be of any kind, 0f, 0x, anything else. When you say that, if I encounter something like ff, I'm going to say that this is a new packet. I'm going to say this is a new packet, and after every value I'm going to index, after this I'm going to index every value just after receiving the ff. So let's say you received altitude, there you received temperature. In this case, let's say you did not receive the altitude, but since it was a new packet, so it says that you did not receive altitude, don't worry, you received the temperature, that's great.
The next packet comes. Let's say this is the FF, this is the altitude, this is the temperature. So it will say that, okay, now it's FF, so it's not temperature, it's new value. So you are going to receive, you are going to decode the new value. So that's why the header thing is really, important. Also in the competition, on the international competitions that I've been a participant of, they say to implement a header, not just a header but a footer format as well. That you're just going to receive a header and say this is a new string, so you're going to decode it that way. And when you'll receive a footer, then you'll say that, okay, this is the string is ended. So any values you did not receive in between is just going to stay at the previous value. The previous value of altitude is 140, so it's going to stay at 140. That means the altitude, after the analysis, after the launch, and after everything, when you have the data, you can analyze, okay, this is 140, this is 140. The time has changed, but the value did not. Basically, we had a packet loss as altitude in this index. See how smart is that? With the simple change of just adding a header and just adding a footer, you are trying to receive, if the value starts from header, it's a new string. If the footer, if you recognize a footer, that means that string ended. You just created something, something that is really good at analyzing the data even after the launch system, even after the rocket launch is completed and after everything, the CAN set is at the ground. When you're going for the data analysis of your, basically, what component was working, what component was not performing well, what happened with the PCB, what happened with the hardware. When you're trying to check up these facts, you'll say that just on the basis of your data, that, okay, I did not receive the data at this point, so maybe there was a problem with your time, the sensor for the time, or maybe the RTC, or maybe there was a problem with the altitude, maybe there was a problem with the microcontroller. So you can deduce just by getting this data in the CSV format, just by adding a header and just by adding a footer. These are the techniques that you have to remember. Okay, so don't worry. Now, in the previous session, I hope you all understood this, by the way. So in the previous session, there was a problem that most of you people were not familiar with Python. And even if you were familiar with Python, you were not familiar with OOPS, you're not familiar with the struct library, you're not familiar with the PySerial, you're not familiar with multi-threading, etc., etc., etc. That created a problem. See, these are the concepts that takes around at least 2 months, 2 months plus, to just master or just complete enough so you can build a GCS. I cannot teach you everything, every library from scratch, every implementation from scratch. Even if you were not to, even if all of the people were to understand OOPS, I cannot assume you all understand the necessary libraries that you need to know the Python, that you need to build a Python as the backend system for your GCS.
Am I audible?
You know how software has a front end as well. A software has a front end that it shows, okay, this is the rocket, these are the values, and then there is your backend that handles the data, incoming from basically USB. So even if all of you were to know the front end, how to code the front end in basically HTML, in CSS, in JavaScript, I cannot assume everybody to know everything. That is the reason I'm trying to teach you guys on how packet farming, how the common concepts, how the similar thing works. I'm trying to teach you what is necessary and what you should at least do at the bare minimum level, so that eventually you can build a GCS on your own. But it is somewhere incomplete. Like, just knowing the theory won't help you build an actual GCS, but just like watching a video on how to write a scooty, you won't be able to write one until and unless you can try and experiment and build yourself. So in this session, or maybe in the future session, I've done something different. Is basically, I'm going to teach you how to rely on AI tools in a perfect way, so that you don't waste your own knowledge. You try to learn something, you try to implement it via AI. Okay, concepts to open Python. Okay, what I meant was actually, this is, let's say this is Python. Okay, this is your GCS. You have to build a front end so that the user can see whatever the actions are happening in the real time. And then you have the backend. So the backend is basically where you try to handle the data, where you try to send the data. When I'm saying handling the data, that means you are going to receive the data from the serial, you are going to decode the data so that the human can understand. You can send this decoded data to the front end. So backend is basically all about handling the data. And when it comes to handle the data, you mean ports. Ports is basically USB. This is where you receive the data from. Okay, these are the steps involved in. So the Python, let's say we use Python and Node.js as our backend languages. Okay, so let's talk about the tech stack for some minutes. So we use Python, Node.js, and stuff like this as our coding language, the primary, programming language for writing our backend scripts. When we use something like that, we need to have the understanding of the similar concepts like OOPS. We need to understand the fundamentals of that programming language. We need to understand the libraries that we are going to use to code, our backend or maybe our front end. For let's say, for example, we use HTML, CSS, and JS in as a front end. HTML for the structure of the page, CSS for styling of the page, and JSS for receiving the data and updating those elements on the basis of that data that you received from the backend. Okay, so there are a lot of libraries. When I say, I mean struct. Let's say this is a library, struct. This is a library that is used to code, basically decode or code, okay, the data that you are receiving. Let's say you're receiving 0a, it will decode it to 63. So that's the use of library struct. Then we use PySerial. We use PySerial for what? We use PySerial to receive the data that is coming from the USB port. Let's say your USB port or microcontroller is trying to send you 0a, 1a, 1b, etc., these kind of values, and it will say your GCS, what will do it will first understand the data from the PySerial, that it will give the similar data to the struct, and then whatever the decoded data is, it is going to save it at the same time, and at the same time it's going to give it to the JS, and JS will send to the HTML to update it. So in the front end, you will see altitude is equal to 23. Not so much complex, right? So you have to follow a certain set of libraries, a certain good combination of libraries and frameworks, so that you can build a stable ground control station that is, at least reliable enough so you can depend on it. So that's what happens, right? So I cannot teach you everything. I cannot teach you the complete Python and OOPS fundamentals. I cannot teach you the Flask. I cannot teach you Socket.io. I can tell you there are certain kind of important libraries that you have to learn on your own. But still, for the sake of this lecture, what I will do is I'm just going to cover up the basics enough so that you can understand the basic fundamentals. You can understand the basic fundamentals. You can understand, or you can just take notes of where does the error occurs. In most of the cases, what are the error prone areas? So you can already counter that. And after that, I'm just going to explain you some tools like GitHub that will help you maintain your software. And then I'm going to explain you about some AI tools like Anti-Gravity and Cursor, so that within the combination of these tools, you can build your own GCS for the first time. And after you start gaining interest, all you have to do is just list up the tutorials of the libraries that you are using and try to build on your own. Okay, so that is the standard concept that I'm going to use. Since I cannot explain you everything, but I can still explain you enough so that you can build your own GCS. Okay, so I hope you guys are feeling a little bit interested now. So we are just going to continue. And should I explain you the statement, how the parser pseudocode works in C++? Okay. Let me just explain it one more time. What does this say? This says that whenever you encounter, in the simplest terms, I'm not going to assume you already know C++ or C. I'm just going to say that in simpler human terms, that the code says basically, if you encounter something like FF, that's your header. And if you encounter an header, just assume and read everything after that. This is your header, read everything after that. If you encounter something like 0a, assume that this string ended. Now look out for another FF. That means look out for different string. And that is all does it says. It will try to look out for byte, and if byte is equals to 0xff, that means if you encounter an header, just read up the whole string, read up all the values. So in that, basically, in this case, you won't miss it. And let me give you an example to explain what I'm saying right now. Let's say this is my name, Gaurav. Now I already know that this is the first character of my name. This is the last character of my name. I know this is last. I know this is first. So if I'm going to, if you're just going to give me something like Gaurav, I will say that this is not my name, or I will also say that U is missing. Something character as named as U is missing. Just because I know this is G, this is V. G is my first character and B is my last character. If I already know the starting and the ending of my string, I'll be able to recognize whether I've missed a packet or whether I received a packet. As simple as that. I hope you guys understood. We can use Java language, we can use different languages, we can also use Go, but it depends upon your tech stack. Let me give you a little information about the tech stack. Okay. Most of the cases, I will tell you to use Python. I will tell you to rely on Python as a backend. Since it's easy to understand and implement. And I will try to say that use the HTML, CSS, and JavaScript as your front end. This is the whole tech stack. And after everything you have built, after let's say the Python backend is working, after your front end is serving great, all you have to do is just package the whole code into a software, or you can say .exe file. The exe file that we used to install in Windows. You are just going to package everything in Elements, or basically, Electron, a software named as Electron. This is basically a framework of JavaScript. So I'm not going to say that use JavaScript as the backend as well. You can, in most of the cases, you should. You can, if you can, you should. But Python is easy to implement, it is easy to understand, it is easy to debug than the JavaScript or than any other languages. Even if you're going to use Go languages for your backend, let's say you're going to use Go for backend, or basically Java for backend or JavaScript, I'm not going to suggest you should use that. If you can find framework enough, so you can just just write code on that. If you are familiar enough, if you know how to create a Java Spring Boot application, surely you can go with that. But it does not really have to do anything with familiarity. It has to do something with how much you understand. Okay. Also, since Python is something that does not take much like kilo lines of code to explain simple stuff, you need just bare minimum, like bare functioning 3 to 4 lines to do a basic process like creating a function. So you won't have to worry about token limits as well. So let's say your Claude is trying to generate code and you will ask it to generate in Python, it won't consume the tokens really fast. So one of the reasons that you should go with Python, HTML, CSS, and JS. So I guess we are done with the frameworks, and I hope you understood this pseudocode. And most important thing, if I have to say that, the crux of this lecture is, one of the important point is finding the signal node in the noise. So you have to implement a header footer knowledge. You have to implement the header footer concept, that you're going to only decode the strings. You're going to initialize a header, you're going to initialize a footer, and you're going to decode the strings in between. Okay, so this is what you should understand by that. I'm just going to skip it. Yeah, checksum, validation, trust, but verify. Checksum is something else. It's basically another way of saying that, but I would say this is something that you should give it a try. You'll be able to understand it yourself. Basically, it's just that we do some calculation at the PCB end, we do some calculation at the GCS end, and we just try to match that calculation. If basically it's 23 here, 23 here, that means the whole packet is received, and that's all it says. Okay, that is checksum validation. I would suggest you to read it by yourself, but the more since there is something you have to calculate, so it gets a little complex. Not for you, it's easy to implement. Since the header footer logic is little bit, just I can say a little bit more harder than implementing the checksum, but it pays you the trade-offs. Okay, so you get the trade-offs well. Now, ring buffers prevent data loss. Serial ports have finite hardware memory. If your software relies on slow pooling loop, the write pointer laps the read pointer and overwriting read-unread data. That is buffer overflow. The GCS sends you, the Rocket sends you the data at the same time the GCS is trying to send a command. The GCS says release parachute, and it will say 23. That means altitude, temperature, and it will say release parachute. The GCS will understand release parachute 23. The Rocket will understand 23. That does not make any sense. That is what basically known as buffer overflow, or basically overwriting the unread data. So what I told you earlier is a perfect example for that. And below is an example of how we implement the serial, basically how we implement the serial library in Python. If you're already familiar with Python, you can understand the syntaxes of Python. And what we are trying to do here is, this is the serial data. Serial data has a function named serial.serial. You can just pass in your port like COM3. In Windows, you use COM3. And then you can pass the baud rate like 9600, whatever the baud rate your, I'm sorry. Sorry. So this is your baud rate that is already coded on your microcontroller. So you just pass in a variable like, let's say, data, which is equal to, you're using the serial library. You are asking a serial function to read the data coming from this port, this USB port, and this at this baud rate. And you're trying to create a function that says, when you receive a data, just append the data inside a buffer. Let's say I'm trying to receive 1, 2, 3, 4, 5, 6 really fast, and it's really fast. I'm trying to receive all this value. These are not just value, these are packets. These are different packets, each of 72 bytes. I'm trying to receive all of that. What I'm going to do is just store all these packets inside a buffer. What happens is, after that is, after I store every bit of value, after I store every value inside a buffer, it will just simply, if I just going to miss certain kind of values, it will load the value from the buffer. Let's say I stored the last 5 values and it did not receive the 6th value. I'm just going to show the string 5th of 72 byte that is stored inside the buffer into the GCS. I'm just going to send it away. That way you will be able to realize that if, let's say, at this instant the time was 0.01 seconds, at this instant the time was 0.01 seconds, this instant the time was 0.02 seconds, you will say the time did not increase here, the values did not change, any of these values did not change. That means this value was taken out by the buffer. So all you have to do is assume that probably your sensor or Zigbee didn't work out, so it didn't receive the data. Okay, these are the kind of triggers that you'll set into your backend. So 5 common traps in the serial communication. What happens is, either wrong baud rate, 9600, 19200. That is the synchronization problem I already told you. Missing start bytes. Let's say you did not verify the FF, or you can say headers. You did not verify the footer, so you can have problem decoding the missing packets. And buffer overflow. Software read too slowly, the oldest data permanently overwritten. Basically, the software is not able to keep up with the data speed, and that is one of the issues of wrong baud rate as well. Ignoring checksums. Basically, the checksums is basically one of kind of validation. You can either just go with this way, this method, or this method. Though checksums are really necessary, you should at least keep them. Ignoring checksums is basically you should keep. Remember, I told you you calculate some certain kind of value x here, certain kind of value x here, and you just try to this is your data. On the basis of your data, you just create a formula and you try to calculate x. You send x here as well. It will try to calculate its own as on the x on the basis of the same formula here. And if the x meets, it will say that the data is received. The data that has been received has no packet loss. Okay, so you don't have to ignore checksums. So do implement it. Blocking reads. Wait for the serial port freezes the entire ground control station UI. Okay, waiting for the serial port freezes. Sometimes there has been a problem that the serial port did not try to receive the data, and as soon as you decounter it, as soon as you counter that the serial port, you implemented a library python serial.py, and even though the data is being received by this serial port, the Python is not able to recognize it. So that is basically the problem of blocking reads. So all you have to do is just replug it, okay, or just restart your GCS as quick as you can. Hope you understood these concepts, and it is going theory on theory on theory. So here is the practical. Should we try the practical? Yes. It is used for error checking. Checksum. How can we detect a garbage value? If the graph of the temperature and the altitude will be on the same rate, and if we saw a sudden decrease or increase in the graph, it means we have garbage data. If I'm not wrong. Yes, you're right. What do you mean by checksum, sir? If FF is frictional force. No. FF is not a frictional force. FF is something like a header format. What I was trying to say is you just try to match the patterns. Let's say X01. This is a pattern. You're trying to look out for this pattern. As soon as you encounter this, you are going to assume that everything after this is going to be a string. Okay. If you don't encounter this, you are not going to read the string, and that will help you prevent data loss. That's what I mean. That is what I meant. FF, it's just another what I should say, another example of this symbol. Either you are going with X01 or either you are going with FF. Okay, this is just an example. So yeah, great. Finally you understood. Now, since we have already implemented, since we have already understood, first we are going to understand what is written in the code, and second I'm going to implement it. And I hope all of you should see. Basically, let me decode this code right in front of you into a format where you can understand. So even if you don't know Python, you can understand what does this code says, right? Okay, so it says that import serial. Serial is a Python library. Now, what was the use of Python PySerial library? This is PySerial. We install this library in our system. We import it in basically our environment. We say that we are going to use this library. We are going to use the functions. We are going to use the capabilities of this library. So what does this library help us to do is the serial library help us to read data from USB. UART. Okay. Universal, it helps decode the universal format of data acceptance via your ports. In Windows, you have your ports like COM3. In Linux, you have your ports like dev/tty ACM0. It's recognized that way. Similarly, in the simple terms, when I say if you just plug your USB into your phone and connect it via on your laptop, you'll just say that it will say your device X has appeared. So device X is basically the name of USB when you connect it with something like Uno or Arduino. Am I right? Yeah. So that is the whole process of the serial library. Then we have struct. Struct library is used in Python to decode the bytes, basically bytes like 0A, 1B. You are not going to decode every byte yourself, so you use struct. The struct library helps you to decode 0A into human readable format, like let's say numbers like 78, 12, 83, etc. Okay. Now stream is a common form of example, basically a common terminology that we use. We say this is data, this is your data packet, this is your data packet of 72 bytes that is you received. You can also call this a packet. And if you are going to receive this packet multiple times, like 72 of, you are going to receive packet A, B, C, everything every second, and all of them are going to be of 72 bytes. You can just call it as stream. This is a data stream. Okay, so that isn't just a terminology. So you can just also just write data. What does it say? That use the serial library, use the function of serial, use this function serial of this serial library. Notice they have S capital and S small here. Okay, so this is different thing. So it says that use the capability, which capability? Serial function of this serial library, and pass in these values. This is, let's say, your connected port COM3. Basically your device has 2 to 3 USB ports. Mine has 2. Okay, you probably you can even have one. So basically these USB ports have certain kind of number. If you try to give it electrical signals, like if you try to connect something like a microcontroller, it will automatically recognize and it will assign it a port, let's say COM3 in your Windows. Try to go to your device settings, try to go to settings and hardware on your Windows, and try to look for connected ports. You will see that if you connect a ports, if you connect your Zigbee, or mainly if you are familiar with Arduino and the code editor of Arduino, if you are already familiar with that, you must have understood what I'm trying to say here. You just passed COM3, you just passed in the correct the current connected port, and you just passed in, let's say the port is trying to say the values that are fast as 115200, so you set the values as 115200. Then you say that stream.read 78 bytes. Just similarly, we are not going to implement header, we are not going to implement footer here, since it's just for example. We'll see that just read 78 bytes, read 78 bytes, that's it. Just read 78 bytes from whatever you have received, and it will say that altitude bytes are going to be bytes from 2 to 6. Let's say it read 72 7A, B1, C2, okay, and C4. It will say from 2 to 6, probably this is the sixth value that says 61. From 2 to 6, it will say that just convert, these values are going to be of altitude, so store them, store B1, C2, C4, 61 inside altitude. Okay, so altitude bytes is basically these are the bytes. From these 78 bytes that it just received from the connected COM3 port at this baud rate, it is just going to read the 78 bytes, and out of those 78 bytes, from the bytes 2 to 6, it's going to assign these values to a variable named altitude, and it will say that altitude. Now this is just then altitude bytes. These are again bytes. You have to convert it into human readable format. So this is basically what you are receiving. This is what you are receiving from 2 to 6. It's not V1, C2, C4. It's basically like X00, X00, X80, X3F. This is what you're receiving. Can you understand that? I cannot. So I'm going to use struct.unpack. Remember what I told you about struct, why struct is used? Struct basically is used to convert the data from bytes to integer, float, etc., etc. You'll just say struct unpack. Unpack basically you are going to unpack the byte format. Okay, so for this you just say that you just pass in two variables. Now what does this means? This is the delimiter. That means that whatever you're going value you are going to receive is in bytes. Okay, and you are going to convert in floats. Float is decimal number. So you will receive value, let's say X003, you are going to receive this value, and it will say that if you are going to receive values in bytes, you have to convert this value in float. Okay, so that does what this NF means. And after that, you are just going to pass where you are receiving the value from. You have stored the value of altitude bytes inside a variable named altitude bytes. So you're just going to pass into that, and you are going to pass the first one. You won't pass all the bytes that you are receiving. You're just going to pass this one, the first value. Okay, so it's going to convert the value into 1.0m. It will say the print altitude, whatever you have decoded from struct unpack, and just give me the value, print this value. So this is what the code means. Now should we implement it? I hope you understood. Okay, so I'm just going to share my screen. To a VS Code editor, and we are going to implement. Finally, I hope since you understood this code, we are going to implement. But I'm going to tell you this before I implement that. It's just that the code won't run. The code won't compile. We'll have problem getting an output. And if you can guess why is that? the single problem that I can think of is I don't have the microcontroller pre-programmed with me. I currently don't have a microcontroller. Though in the tomorrow session, I'm going to show you how this works. So probably you can just wait up for that. But still, if you want me to implement, I'm just going to code it right away. So you won't have a problem saying that he just wasted our time teaching us theory lectures. Tinkercad is different. Tinkercad is different. Let's say Tinker is the Python library that is used to create a GUI. We have already come, advanced frameworks. We have already advanced languages like HTML, CSS. So we are probably just going to use that. Also, Python, basically relying on Python's GUI in our cases is going to be a problem. So I hope you can see this. Let's just say I'm going to create a new Python file, test.py. Does that sound right? Test.py. This is what I'm going to create, and I'll say, I think, if you guys can see the screen, is the VS Code screen visible, guys? Yes. Opinion on Thorny, you can, yeah, definitely. For the ideally, you can use any ideally that you're just familiar with. Use anything that you can. But since I'm familiar with the VS Code, I'm just going to create a new file and I will test it out. So first thing, what we learned is we have to import the library. But even before that, I'll suggest you to go on your computer screen, just open CMD admin in your computer and just type in these things. You just type in these commands. What commands you have to follow? You'll just first say pip install py-serial. It will install the serial library. Okay, so you're just going to write pip install py-serial. Next thing you are going to use is you'll say pip install struct. These are the more libraries. I'm going to just tell you the use cases of each one. So just please, I hope you guys can see the screen. I'm going to just tell you the use cases of each libraries. Next thing you have to know is you have to install pip install Flask, and then you need to install pip install Flask Socket.io, or I don't know if it's this. I'm just going to keep it this. Okay, so these are the libraries: Socket.io, Flask, struct. Then you have some built-in functions, built-in libraries, so you don't need to understand, you don't need to install that. What are that? You have time already built in, it's already a built-in function, OS, threading, thread, basically, etc. So you have these kind of libraries built up. So these are the built-in libraries, so you don't need to install. Rest all of these libraries, just go to CMD admin and run these commands, and you will be able to just code whatever, just implement whatever I'm doing. Open up any kind of editor that you are familiar with, and just write in this. First, we are going to write serial. Serial is basically from which we are going to catches, basically reads the data from USB ports. In my case, since I'm using since I'm on Ubuntu, which is a Linux distribution, so I have the ports connected in different format. The code for my port is different, but surely you can, if you are on Windows or even if you are Mac, you can just check your ports. So I'm going to run import struct. This is the second library, and I will write in, I'll say data. What my data would be? Does anybody remember what the data should be? Firstly, I'm going to read the data. I'm going to read the data. How I'm going to do that? I'm going to use serial, the function from serial library, and I'm just going to say that read the data from this port, /tty acm0, and I'm just going to pass in some baud rate, let's say 9600. And then next thing, I'm going to create a packet. Packet means I'm going to read something from this port. Okay, so data is something, data is a bunch of collection. You are just getting like thousands of values data continuously. So what I have to read is, I'm just going to read stream.read. I'm just going to use basically data.read. How many bytes? Let's say for an example, I'm going to read 12 bytes. So I'll just write 12. So I'm just going to process these 12 packets that I received from data. And where did I receive from? I received from the serial library function by passing my current port number and the baud rate. Okay, so baud rate should be equal. How should I say this? Baud rate should be equal on both microcontroller and GCS backend. For example, we are going to just consider this is the backend. We are trying to write a backend that handles the data from the CSV port, and that what we'll do is just we'll create alt bytes we'll say that alt, our little variable, is going to just read packet from 1 to, sorry, it's going to read from 3 to 4. So these are the packets of an altitude, and then we are just going to write altitude, which is equal to, we are going to use struct library, struct dot unpack, and we are going to just pass in a delimiter. That means we are trying to decode the bytes, and we are going to convert it into floats, and then we are just going to pass where the data is coming from. It's coming from altitude, and after that we are just going to use print, and we are going to print this altitude. It should be an f string, altitude of what, alti. I'm just going to name it alti. Okay, so I'm just going to run this code, run this Python file. Obviously it won't execute, but let's see what's the error is. We'll surely understand the error. It says that the let's understand the error. What does it say? It says that the file this that you're trying to code, the data, it has a problem with this line, data serial, because it says basically it says that, yeah, the serial exception message error could not open port. It says could not open port because the port is not connected. I have not connected any kind of device in the system, so that it's not able to recognize the port. But surely, even if you are connected the device, you should know that which port number your device is currently connected on, and you can just Google up for that. I don't know how to do it in Windows, but I surely know how to do it in Linux. So you just run in few commands and you just say that what port is available. Okay, so yeah. The next thing is from raw bytes to system architecture, that we have already discussed. The system design for ground control station. Here I was going to discuss how we look up for different parameters like ingestion, how we ingest the data, how we process, how we store, how we present in the UI. And then, see, we are trying to do so many things together. We are trying to pass the telemetry. We are trying to update the UI component A. Like, let's say we are trying to just understand what is the data in the backend. We are trying to send the data. We are trying to do everything in just under 1 second, since we have to receive the next data as well. No, so that is what we do. So we have to implement a system design for that. But surely we are going to understand these concepts quickly within the first hour of the tomorrow session. In the next hour, we are going to implement it, and we are going to understand how our UI looks like. You see how we implement graphs, what changes we have to make sure. What changes we have to take care of beforehand, so we don't have to face something like, see this smooth graph updates and see this is blurry graphs. You can not really understand anything from it and stuff like that. We are going to just cover everything in the tomorrow session. So until tomorrow session, I will just tell you to revise everything. I'm going to share the notes, revise whatever I've taught up until now, and just try to implement this code, a small line of code, to understand decode the value of altitude. And we'll probably meet in the tomorrow session. Let me just show you what are the slides of tomorrow session. So I'm going to stop share and reshare this again. If you do have any doubts, just please share with me in the comment section. But yeah, so this is in the tomorrow session, this is what we are going to discuss. See, the current data pipeline. You have something like, you receive the data, how you parse it, you check for header and stuff, and then you create an event bus. You do different things like you update the charts, you update the graph, you update your CSV, the CSV file that data is coming, you update the WebSocket, you push data, like you push this data to the front end, and you have the real world architecture. This is an example of what I created, the Vajra.js in the Turkish Rocketry, in cancer competitions. So I'm going to share the GitHub link, and you can just watch it from there. And in the tomorrow session, we are also going to discuss about the UI, the GUI of this software as well, and what things we take care of. And then we have the backend. We're going to implement the simplest backend, so you can just understand how backend functionality works. And then we are going to use some AI tools. And see, this is an example of how our export. This is how it looks like. This is your USB, and it is connected via an USB. This is your Zigbee. It's connected via an USB to your laptop. This is the USB interface that I was talking about. Okay, so if you connect this, you get a certain certain port number. Let's say COM. I don't have my pen right now, so you get a certain port number like COM3 or COM4 or COM11, whatever it is, if you are on Windows. So you have different approaches. You can use Node.js as your backend as well. You can use Python as backend as well. Of course, you can use multiple languages as your backend, but these tools are the familiar ones that are tried and tested by me. So I can just count on that. Also, if you have understood anything from this lecture, just try to share it in the comment sections. If you haven't learned anything from this lecture, if you are still struggling to understand something, please tell me. Data.read 12. What is that 12? 12 is basically we are trying to read those 12 bytes from the bytes we just received. Let's say we received we are trying to read 12 bytes. In our example, we are trying to read 78 bytes, but we are trying to read 12 bytes. Now request the coordinator to just ask for the doubts, so people can ask doubts with their mic open.
All right, sir. So shall we begin with the Q&A?
Great. Siddharth
So-
says very informative, learned a lot. Great. So please suggest some which we need to revise for tomorrow's lecture. I'm going to give you notes. Topics. Yep. I'll give you notes. So whatever you have read on today's session, you just have to revise it. Yeah, I'm just going to share the all the important algorithm that is required in the tomorrow session as well. I think you can go, request the host to conclude the session, please. I'm interested in both the AIML space. Don't worry, just stick up to whatever I'm teaching right now, and I'll explain the AIML applications, simultaneously. So you'll have understanding the fundamentals and building as well. Okay.
Thank you, sir. Thank you, all the participants. Now you
Thank
all
you
may
very
leave the
much
meeting.
for attending the session.